in this video today I'll give an introduction to injectivity, which is a very, very hot topic among reservoir engineers, managers, and anyone interested to start polymer injection to enhance our recovery. So as you will see in the next couple of slides, there are few things that you have to take into account. And one of them, of course, is field evidence, to make sure that you gather enough information not to stop at the simulation or at the laboratory and actually try to get real values. So I hope you find it insightful, and if you have any questions, I'll be very happy to answer them. And to let you know, so this is a small part of the training course and seminar that I have on polymer flooding from A to Z that covers both the screening, the design, injection parameters, then the laboratory, simulation, economics, reservoir response, field cases, and a little bit more. So let's go. Polymer flooding, injectivity in polymer floods, and interaction. So, as I said in the very beginning, it's a very hot topic, and the main reason is very simple, is it will condition how much oil you can produce. It's a mass balance, so if I can't inject much, I won't be able to produce much, and the idea is to understand during the course of my project and during duration of polymer injection is try to understand how things will change. So it's very difficult, of course, because it depends on the reservoir characteristics and a variety of things, but this is quite important. So for polymer floods, and because the solution is more viscous, this is the main reason why people fear or anticipate differences with water injection, because the viscosity of water is low, even lower at high temperatures. And with polymer, when you go from 1 centipoise to 5, 10, 20, 50, then of course it is normal to anticipate a change in reservoir response because of the viscosity. So the problem I see, and one we will discuss here, is when models are preferred over field evidence, and this is something that prevents people from trying, and very often they stay at the stage of simulation and lab and they miss the chance to really get amazing results in the field. So the question here is, why is it difficult to predict injectivity? So of course, when you go from polymer solution 5 to 20 centipoise and you start injecting, the question is, what kind of response will I observe? So is it a pressure increase, pressure decrease? The pressure won't change. Will my injection rate change, and how much and for how long? So I would say there are two ways to try to get some injectivity values. One of them is you try in a model to try to predict what will happen in the field if you start using laboratories that you have gathered in the lab. And so you build a model, you run with your constraints, so it can be bottom hole pressure or injection rate or both. And then you see what is expected from the simulation. And then you can decide yes or no to go to the field and try. And there is the other option, which is, well, I don't have a model, it happens. Or I know that it's been very difficult to predict injectivity with any of the available simulators for many reasons. And so I decide to go in the field. I gather the values which are the most important that you can't get in the lab. And then I will update my model and build my business case using these values. So very different approaches, but both exist. And so of course, one of the questions in the end is why the expectations are always rather different and quite different from the field data, which is what we'll try to answer in the next slides. So the question with injectivity is what happens in reality. But before that, we probably need to have a quick look at the injectivity equation, because you will see it's rather important to understand what can change and how things can change. So the equation injectivity is rate divided by pressure reservoir minus pressure downhole. And if you want to get all the values right, you will need at some point a pressure gauge. And when you look at the equation, what is changing? So you have, of course, the viscosity, which is here described as water, but if you switch to polymer, it will become the polymer viscosity. You have the skin, you have the radius, you have the height, and you have the permeability among the most important parameters. A couple of questions is maybe first one is, what will be my real bottom hole pressure? So if you have a gauge, you don't have the problem. But something people forget that will mathematically impact injectivity is called the friction reduction or drag reduction effect. It's well known by the people into the fracturing industry because polyacrylamides are used to decrease the pressure drop. So you put a little bit of friction reducers into the water, anywhere between 50 to 350 ppm, and you will observe a pressure drop decrease from 50 to 70%, depending on Reynolds number, concentration, water quality, etc. But this is important. And we could say, well, it's low concentrations, so it works. But it does work too at higher concentration. And I'll show you examples. When you have 10, 15 centipoise, the pressure drop in the pipe with polymer solution can be up to 70% lower than the pressure drop with water. And this will mathematically impact the injectivity because it will condition the pressure that you will have just before entering the reservoir. So how does the pressure change inside the reservoir during polymer injection? It's something that difficult to answer, but you will have to monitor closely over time. Then what is the effective permeability to water, which is also something that sometimes we don't really well understand, that will impact especially the real perm, the efficient mobility ratio, and what we need as a target viscosity. What is the real in situ polymer viscosity? Because in the laboratory what we have are viscosity curves, but this will not be exactly the same values in the porous medium between viscosity in the rheometer and in situ viscosity, because you have retention, you have changes of permeability, of saturation of fluids. So this is not considered and will have an impact also very much on the effective in situ viscosity and of course the pressure buildup and the oil recovery. And how does radius and height change over time? Because the idea with polymer is you will change the sweep efficiency. So both the area contacted vertically and aerially will change and impact the pressure. And unfortunately, this is not something that we capture very well in our 3D models just because of the size of the grid, how much we know about the reservoir, and often underestimating the heterogeneity. So let's start with a very simple question, which is also very important, is what is a good injectivity? Because in a lot of cases, the well or the wells are taking a lot of water, but with a very poor sweep efficiency. And so the idea is, when you look, for instance, at this slide, is you have water injection and you have created fingers, especially in horizontal wells with heavy oil. And so the water, you are basically recycling water through a couple of fingers, and so you can inject a lot of water, 200, 300 cubics a day, but it doesn't mean you are recovering a lot of oil. Otherwise, well, maybe you would not be considering an install recovery techniques at all. So maybe a good injectivity would also be an injectivity where you have a good sweep efficiency. And in that case, losing injectivity would be a problem because you would not be able to recover as much oil. But in that case, the one displayed here on the slide is, if you have a lot of water recirculation and very high water cut, then maybe losing a little bit of injectivity while observing a reverse trend in water cut and oil cut is not a problem. It's maybe even what you want to observe. So that's something which is quite important to understand. So some injectivity issues and considerations. So again, depending on your baseline is injectivity issue, but compared to what? So the idea is if I have a bad sweep and I know I leave a lot of oil behind, I might not be afraid to lose 20% injectivity if my water cut goes from 98% to 50% for 6 months, for instance. So again, injectivity as a word doesn't mean much if you don't know precisely the gains you can obtain if you reverse, for instance, the water cut trends. And of course, a clarification is required in the first place, which is what is an injectivity issue during polymer, because it can be linked to the polymer, but it can be linked to the water quality, which is changing, wellbore damages, or change in fluid flow. So it's important to understand when do you see the injectivity decrease. So if it's from the very beginning, if it comes after some time, or sometimes it doesn't come at all, which is really important to understand also. So in that case, if injectivity decreases after some time, we will see in the next slides, it just might be the sign that you are mobilizing an oil bank and the project is working fine. So that's probably not the kind of problem we are we're not trying to solve. So what could be the factors that will impact, of course, the injectivity? We will, I would say, split into 4 categories, but if I had to put some keywords, it would be, of course, the reservoir, geology, heterogeneities. You will have the fill-up, the voidage replacement ratio. Then you will have the rheology of the fluid, the viscosity. You have, of course, the water quality, and anything that will be in this range. So the oil in water, the solids, the combination sometimes of solids and polymers, and etc. So these are some of the important things that you need to understand and maybe be sure they are under control to avoid any unexpected problem. So again, some other questions, and then we will try to go through some examples, is how can my injectivity predictions be reliable if I don't take into account drag reduction and the non-Newtonian behavior of polymer solutions? Do I precisely know what will be the shear rate and viscosity downhole? So we might know the shear rate, but what we sometimes forget is the polymer solution we use in the lab to characterize, I would say, the future efficiency of the project, and the one in the field will be slightly different because water quality will be different. The polymer solution will have been through some pumps, a little bit with very slight changes. So the idea is, how do I make sure that I know precisely what will be the viscosity and the shear rate before it enters the reservoir or once it has entered the reservoir? This is of course impacted by the well completion, the perforations, their density, how clean they are, which is, we'll see in the next slide, very important to minimize mechanical degradation. And just also something important is I always see people using initial reservoir temperature. And but if you have 20 years of injection, and if during summer and winter the water temperature changes, you might be stressing the reservoir and creating micro cracks that in the long term will become bigger cracks. And when you switch to polymer injection, then you have already enhanced the path to the reservoir, which is very important for the polymer itself. And this is what I want to say at the last slide, is what happens if you have fractures and microfractures. And you will see that basically some of the keywords become irrelevant, and one of them is shear thickening, which is when you force the polymer solution at very high rates in cores in the matrix, and when you see that the pressure is going to the sky before you break the chains, and then see again a decrease of viscosity in the core. So what could be the definition of an injectivity issue for polymer injection? So there might be the case where you have the water baseline and now you start injecting your polymer. So the first thing that you might see is injectivity will decrease dramatically upon commencement of polymer injection, and this is of course something that you don't want to see or you need to understand very fast. And very often I call this scenario the simulation scenario, because in all the simulations I've seen, basically this is what happens. So the moment you switch from water to polymer, the simulator will tell you that you will reach the maximum pressure very fast, and it will automatically decrease the injection rate, which you might see is probably something we have never seen in any of the field cases around the world. Maybe a couple of exceptions, but they are really exceptions. So then there is scenario B, where the injectivity starts to decrease after some time, which is just meaning that you might be mobilizing an oil bank and everything is working very fine. You have no problem. So the only question is how much injectivity can you afford to lose, which is a different question. And then there is D, where injectivity barely changes or increases over time. And that might be also another question, is what's happening? Am I creating or extending fractures? Or do I really know how much sweep I have? Is it going in the layers I think it's going into? It's been the cases where sometimes there is more than one layer, or we think it's going in one direction, but it's going in many others. So, and then there is D, where basically the injectivity increases also very fast. It can be a problem where here you might have created fractures, but the question is how far they've been. Have they broken through the caprock, or is it just something that maybe you were expecting, or that you want to create a pre-frac to enhance the injectivity? So if I have to summarize these possible explanations, so there will be factors linked to polymers, factors linked to reservoir, water quality, and of course the geomechanics, and obviously the history. So before polymer injection, what has happened? How was my voyage? Did I create some preferential path, and in which directions, etc. So you will see that the most important things in this area are basically the presence of fractures that we will discuss a little bit after. So what are the mechanisms affecting injectivity? And this is where I said I split into 4 categories. The first one is basically water quality and everything linked to the fluid itself, but which has nothing to do with the polymer. The second will be the polymer-related mechanisms, including rheology, degradation, drag reduction. Then you have reservoir-related mechanisms, which is probably the most important, is the near wellbore area. So is it understood? Is it well characterized about my perforations, the existence of fractures or skin, or both, depending on the wells? What about conformance? In unconsolidated, do I expect some changes, decompaction, compaction, dilation? And obviously the geological uncertainties. This is extremely important because if you use simulation, depending on the size of the grid, you might underestimate the local heterogeneity, which will be very important to characterize the injectivity. So we come to reservoir simulation, which is what are the assumptions, and what about the data quality and everything else. And so the first one here will be basically the water quality. So it's quite important to understand that in polymer floods, if the water before was, you could inject it. Normally there should not be big problems during polymer injection. But sometimes, for reasons, you have some synergies between the presence of polymer and solids flocculations. And so in the long term, you might observe injectivity decrease. And the idea is, of course, to control the water quality. You don't want to build the skin and anything that you might have to treat afterwards using acids or controlled fracturing or anything like that. So it's very important to minimize the growth of bacteria, the presence of oil or solids in water. You know, you have cases sometimes where the production plant is releasing slugs of oil that wasn't treated, and it goes into horizontal wells where the velocity is low, and basically you accumulate oil and you build a skin that is then very, very difficult to remove. So this is what is basically shown on this slide. So building a cake. So that's something that happens, of course, during water flood. And we don't like that during water injection either. But it means we also don't want to observe that during polymer injection, because it will just create problems that no one needs, basically. Then there is the impact, of course, on relative permeabilities when you have oil residual into the water. So that will, it can just decrease your effective permeability to water and build pressure, but for the wrong reasons, I would say. It's just because you can't propagate efficiently your fluid. So it's very important to get the water quality under control. And here I'm not mentioning oxygen, which impacts the polymer solution. I'm just mentioning I would say, what's even important during water injection. So the next step is polymer-related mechanisms. And it's very, very important to understand the rheology, and especially how it will be in the field compared to the lab. So in the lab, very often what we tend to do is to run core floods at fixed velocity in the beginning to check propagation and retention, and then making in situ rheology profile by increasing the velocity. And so typically what you will see is at low velocities you have what's called a Newtonian plateau, which is once you have low shear, which should determine at your reservoir conditions. If you increase the velocity, then you will go into the shear thinning. So the velocity increases, the viscosity decreases. And this is normally reversible. So it means if you stop shearing, you should go up again and reach the Newtonian plateau. And then at high velocities, you reach a Newtonian plateau again. And if you are in matrix conditions, normally you should observe shear thickening, which is you push the solution very hard and the polymer has no time to go through, to relax and to conform. And so basically you will observe a very drastic pressure increase until you reach a point where you break the polymer chains and then you lose viscosity. So this part on top of the shear thickening is not reversible. So it means if you go back, you will have a much lower viscosity at Newtonian plateau than the one you had before degrading the polymer. So this is of course important to understand. The question is it happening in the field? And so in the laboratory what we have is a very simple, very often homogeneous core, and you have no perforations, you have no fractures, you have none of the near wellbore effect that will be extremely important for the polymer. And so very often what we have in the field is microfractures or fractures, and even perforations, depending on the length, can be considered as microfractures that will allow the polymer to get inside the reservoir without being mechanically degraded. And because something important you will see is once you enter the reservoir, the shear rate decreases very, very, very fast. And so the idea is shear thickening only happens at high shear, but if you have some fractures, then the shear will decrease fast. And once you enter into the matrix, basically, you are safe and the polymer is safe, and then you can really avoid this mechanical degradation. So that's why it's important to understand the shear profile in the well, in the perforations, and for vertical wells. For horizontal wells, very often the shear rate is extremely low, so it's not the kind of problems we are investigating. So among these polymer-related mechanisms, so this is continuity of the previous slides, which is, so shear thinning is basically something you will observe once you start pumping the polymer down to the near wellbore area. And then as soon as the rate decreases, you are going back to the Newtonian plateau and you start in the reservoir to push the oil out. And so something which is also important to understand is there is always a difference between the polymer solution we prepare in the lab and the one we have in the field. So in the lab, it's pristine, there is no degradation, it's under control, the batch, everything has been quality certified. So for quality, it's the same in the field. The difference is basically once you start going through the pumps and through the perforations, you will start removing the very high molecular weight chains, which often are the ones that cause trouble when it comes to injectivity losses and plugging, etc. So if you cut these chains, you will also switch or shift the onset of shear thickening in that case, and the viscosity curves, the in situ, rheology profile will shift, which is quite important. So that's why a slight change in the polymer solution characteristics will have quite an important and substantial impact on the rheology inside the reservoir, which is something that it's good to understand. So the rheology in the field is, as I said, is the flow when you have perforations in vertical wells is not completely radial. It's pseudo-radial, so you have fractures, linear flow, and if you have fractures, the question, of course, depending on how far they go, you will minimize mechanical degradation, enhance the injectivity, and you will maybe not observe the kind of pressure response that you were expecting from the simulation, which is very often what is not being considered. So if I look at this slide again, what should be remembered is if you have fractures perforation, shear thickening disappears. Then the shear rate will decrease very fast, as you see at the bottom of the slide on the graph, which is 3 meters away from the wellbore. You are below basically 100 reciprocal seconds, and then below 10 reciprocal seconds, which is too low to observe any of the shear thickening effect that we can observe into the core without the presence of fractures or any of the features that will condition the way the fluid gets from the wellbore into the reservoir. So for horizontal well, it's a bit different, I was saying, because the rates very often are very low, and it's rare we have to look for shear thickening in this case. So one of the other very important parameter that I discussed a little bit before is drag reduction. So the drag reduction or friction reduction is a phenomenon which has been understood or discovered in 1949 by Toms during the time they was manufacturing napalm. And so what was observed is when you put a little bit of polymers inside a turbulent flow, so the fluid in turbulent flow, what you will see is a pressure drop decrease. And so there is quite a lot of evidence today. It's used in a lot of applications. One of them is hydraulic fracturing, where you use polyacrylamides or other polymers to decrease the pressure drops in pipes, the number of pumps used to pump the fluids, and reach much higher pressure rates to break the rocks. And so this is very, very important, because we could think that it only works with low polymer concentrations, but as you will see, it works in a variety of cases, even at much higher viscosities. So if I take an example to make you understand what kind of gains you can expect. So here it's low concentrations, typically the kind of concentrations for the fracturing industry, but here it was for water flood. So by putting 100 ppm of polymer into a water flood, the operator has been able to increase the flow rate by 28%, which is of course tremendous, and it could be a very interesting water flood optimization strategy to when you have reached, for instance, you want to debottleneck your facilities because you have reached max pressure, for instance, etc. It can be a good way to increase the rate by adding a little bit of polymer. So, but in reality, when you look at this case here, so in that case, it was 15 centipoise polymer. And so the upper graph shows in blue the pressure drop with water and in red the pressure drop with polymer. And you see that the space between both curves even doesn't flatten. What I mean is when you increase the Reynolds number, you really gain a lot of, I would say, pressure drop with the polymer solution. So at the maximum, you have a difference of 200 kilopascal per kilometer in terms of pressure drop difference, which is huge. So we're talking, as you see on the graph below, about a 4 inches pipe, I would say, setting. And so the maximum drag reduction obtained in that case was in the range of 70% with a 15 centipoise polymer solution. So I let you imagine what can be the pressure drop difference between a water flood and a polymer flood when you look at what is the pressure downhole. So if it's not measured, it is something very important that will mathematically condition your injectivity based on a formula that I've shown in the previous slide. So it's very important to understand this phenomenon when you want to get your injectivity right, because it might be something very surprising at the beginning when you start polymer injection. So if you switch at constant rate between water and polymer at low concentration, it's very likely that the first phenomenon you will see is a pressure decrease, just because of this effect. And so if it's not taken into account, then you might wonder what's happening, while it's just something very normal which is being used in a variety of industries. So also how to improve, I would say, the flow and minimize the fears is to make sure that you have enough perforations or pre-fracs to minimize mechanical degradation or anything that can, I would say, impact the polymer entering the reservoir. So you have a lot of very simple ways to calculate the shear rate in perforations with spreadsheets. You can see on the right side the difference between large perforations and small perforations into a vertical injector. And so all these things are very, very, I would say, important to take into account. And the best way to avoid studying shear thickening or to be worried about anything in that case is to have enough perforations so they are big enough, or that you have some pre-fracs, control fracs to help maintain the injectivity and minimize polymer mechanical degradation. So something recommended in verticals very often is to have 12 shots per foot minimum, and of course longer perforations. They should be cleaned, obviously, to minimize the accumulation of skin and the polymer being degraded, I would say, when trying to leak into the matrix because there is too much sand in the area. So among the other parameters which are critical, and I've been discussing this a little bit already, is the existence of fractures. So in my experience, a lot of reservoir engineers and a lot of people being afraid of regulation or anyone in the upper management, I would say, don't want to pronounce the word. But when you just compute what we should have based on Darcy's law, just going from 1 centipoise to 2 centipoise or to a resistance factor of 2, we should lose 50% of the injectivity. So interestingly, no one I know has ever observed this in the field. So the question is, what's the difference? And based on all the experience that was gathered and the well test, the sampling and the monitoring, the answer that popped out was basically the existence of fractures. So big, small, we can call them different names. The most important is for them not to propagate too far, not to break the caprock, but it's something that can be monitored, that can be assessed, that can be controlled pretty well and accurately. So the observations, and we will discuss a couple of additional cases. You look at dredging, for instance, injecting up to 300 centipoise with an injectivity just 10% lower compared to the 50 centipoise solution. And some others who have seen permeability increase by what they call shear dilation into unconsolidated heavy oil with horizontal wells. So this is probably the most important feature to explain why injectivity has always been better than expected. So there is some literature on this, and I really recommend to read the papers from Randy Seright, to understand the geomechanics. So this is really, really important to choose the wells, to drill the wells, to use the fractures and understand the stresses, that if you create fractures, they will be beneficial for a sweep. So basically you want them to help you recover more oil. And so this is why you need to understand the geomechanics at the very beginning before you decide to inject polymer and to choose patterns. So what was observed, and these are some results also from the literature reviews, is you can really improve injectivity and productivity as long as you control the fractures. So this is the idea, and you really can get a lot of value for injecting your polymer if you have some, or if they are here, but if you know in which direction they are going, because you will gain injectivity and then you will be able to improve the sweep as long as they don't, of course, connect the injector and the producer. So a couple of cases that you can look at. One is, of course, in Suriname with some horizontal fractures. At OMV also, they have published quite a few papers on geomechanics and fractures, and now they used the simulation to really better capture these mechanisms to explain the very good injectivities in the Madsen field. So that's a very nice example. And also some other cases, I mentioned daging, but no injectivity issue or even fractures compromising reservoir seals, despite injecting 300 centipoise polymer, which is significant. Daging in the case was the oil viscosity is in the range of 10 to 15, and so on permeability in above 400 millirc. So it's something which is in the case in which people would not very often consider injecting more than 30 centipoise without the fear of losing injectivity. But in that case, they had no problem. So will fractures break out of zones? So geomechanics. It's very difficult to predict, but what was observed is that the length to width ratio is in the favor of going inside the reservoir instead of breaking through the cap rock. So it's quite important to understand the direction of propagation should you create some fractures. So we discussed reservoir-related mechanisms. So one of the things I said is important is you have the baseline for injectivity, but you should also understand the voidage replacement ratio, the fill-up time, depending if you start secondary polymer, tertiary polymer, if you had a good baseline, if you had a confined pattern, if nothing is changing in the surrounding wells. So all this will really impact the kind of reservoir response that you will have when you switch to polymer. So, of course, there are a couple of questions left unanswered for polymer. So one of them is, you will see that to get a good injectivity, you need fractures. Luckily enough, I would say, they are here even during water floods, given the history, the presence of perforations, and sometimes the dirty quality of water that has helped build skin that then was fractured to just allow the rate to be kept the same over 20 years. So there are a few things, of course, that you need to capture, which is if you see early polymer breakthrough. So how can you tell if it's basically a fracture or if it's just viscous fingers? So for this, you need very close monitoring. If it will depend on the breakthrough time, if it's right after, for instance, you increase the rate, or if it's after 1 month, 6 months, 1 year, depending on polymer concentration. So for instance, if you increase the rate and viscosity and after 2 hours you observe already a polymer breakthrough with very high concentration, it is likely a fracture. And so the way to also understand is, if you decrease the rate and or the viscosity, you should see a change of the whole plot slope and the fracture closing. So monitoring is key, and of course the timing and concentration. So if you observe polymer breakthrough, you inject 1000 ppm but you produce 75 ppm after 6 months, it's not a fracture. So a fracture will be something that you will see the breakthrough very, very fast if the fracture was here extended or is being created, and with, I would say, quite significant polymer concentration depending on the size of the feature. So again, you could decrease the rate if you have viscous fingering occurring. So the best way to fix that is basically to increase polymer viscosity. And this is very often what we see in polymer floods, which is we see some polymer breakthrough a little bit after a couple of weeks or months after the beginning. And so this is basically because we have underestimated heterogeneity, we have viscous fingers, and so the idea is to minimize any polymer coming in the producers. The ideal case in a polymer flood is to never see the polymer in the producers. So it means taking sometimes aggressive steps to fix the fingers, to fix conformance issues, either by increasing the viscosity and making some slugs to slow down the propagation in these fingers, or to do some spot conformance treatments. So it can be, I don't know, microgels, nanogels, preformed particle gels, anything that can be placed more or less correctly into the feature that causes a problem. And if you have fractures, then it's much easier. You need to treat with a gel if the fracture was here before. And if when you decrease the rate with a fracture and it doesn't fix the problem, you might have also to go with a gel treatment to fix the fracture. So again, fractures very fast. And for the rest, it usually takes several months. So a quick talk about modeling, which is one of the false parameters that can explain the difference between expectations and real injectivity measured in the field. So the first thing is you have to model, of course, to benchmark with the field case. So I will skip basically the methodologies for dynamic modeling, but answering these questions is very important. Is why is the injectivity often much better than expected? You should know how the expectations were built. So there are two kinds of expectations. One is, well, we switch from water to polymer, and since there is a difference in viscosity, then I'm expecting a change of pressure. It is normal. What is not normal is when someone decides not to go to try in the field because the model said that the minute they switch from water to polymer, the pressure will go to the sky, and then the project becomes not feasible. So once again, this has never been observed as far as I know in all the papers that I've read. I missed some, I'm sure, but the idea is you need to benchmark against field evidence. This is very important, because then in the model there are a lot of things that have that will impact the results. So the size of the grid, how much you know about the reservoir, so what is your how did you upscale, what keywords do you use for the polymer. So all these things will have a huge impact. And so what we know is in the field very often and almost all the time, there's been no short-term injectivity issue compared to all the results from simulation. So it's very important to benchmark the model with the field evidence. So, and now, very interestingly, I would say in the last 5 years, more and more people moved a little bit away from 3D simulation to analytical equations to try to better predict the injectivity. It's very interesting because, of course, the question is, well, if I can get in the lab and in the model the most important parameter I need for my business case, so why do I keep using these tools and instead of trying in the field and basically getting the value for my reservoir, for my wells, because the value might also depend on the wells and the reservoir characteristics in some places, in some areas, in some patterns. So it's very, very important to try to build a case, to build a business case, but to say, okay, the model I know based on all the papers available that my pressure prediction might be erroneous and I will have to go to the field to try. So that's all about, expectations, but it's very important not to stop at the model. So you will see in the papers there are different ways to calculate the rheology and the viscosity with these equations and spreadsheets then to try to predict that depending on the radius and the well bore. So you see here we see how fast the shear rate is changing also depending on the distance away from the well bore. You can use these equations to try to build your own spreadsheets, calculate how far the polymer will go based on the layer characteristics, assuming you really have captured the heterogeneities. And so once you have this, you can try to predict basically this kind of curves, which is how much injectivity will I use? Will I use a lot? Not a lot. And so about the important tools that you need to monitor the changes, one is the whole plot. So of course we need steady state to make sure that we get relevant values, but the idea it's a very good tool to see the changes. And so in that case, what's very interesting is if you look at the green curve, for instance, what you see is when they switch from 50 to 100 centipoise, there is no change in the slope. We're doubling the viscosity and there is no change in the slope. But then when they go down from 100 centipoise to 75 centipoise, the slope goes up. So what does it tell us? So it tells that from 50 to 100 centipoise, it was already fractured, and that when we decreased the viscosity, we decreased the pressure, if you want, in the reservoir, then we close the fractures. So that's the best example when you have doubts to check what's the behavior of the reservoir and the response depending on the viscosity or rate changes if you decide to test the reservoir limits. So again, very, very important. And you have the same kind of trend for the red curve, which is you go up a little bit when you decrease the viscosity. So whole plots are amazing tools for that. They have limitations, but they can tell you already, at least if your well was fractured, should you want to test the reservoir limits. Another example, so the pressure here is in red and the viscosity is in green. And you see from time to time the viscosity goes from 12 to 20 centipoise and the pressure doesn't blink. So this means that it's also fractured. There is no change in slope. So that's another great example telling the operator that your well is fractured, but everything is fine because you have no polymer breakthrough, you have no direct connection, you still have you will have extra oil, but in that case the pressure should not be a success criteria to assess the efficiency of polymer injection into this part of the field, which is very important. There are cases, for instance, like Salim in Russia, where the operator has used controlled fracturing to enhance the injectivity. Reason was the beginning of poor water injectivity, so of course it would have been difficult to inject the chemical slug. But there are a few studies out there showing how to make controlled fracturing to enhance the injectivity and bypass a cake if it's something has been built over the years. Then there is the case of unconsolidated reservoirs. So fractures in unconsolidated, as I discussed on other video, is a bit more difficult to picture. Between maybe can be some dilation, decompaction. So depending on geomechanics, stress direction, you might still have preferential geometries of the features for sure. But so what we see very often is when you let the time for the reservoir to adapt to the pressure, you can reach much higher pressure in unconsolidated than one you can see, of course, in consolidated reservoirs. And so the way you determine, for instance, the frac pressure in unconsolidated might be misleading when you start polymer injection if you have very, I would say, slow and progressive injection, and the reservoir has time to adapt, I would say. So really playing on geomechanics in that case can favor, you can maintain good injectivities. Couple of cases, so it's always interesting to see the publications and the reaction of operators before and after. So in that case, in the paper, the authors say they report an unexpectedly high well injectivity, and later a decrease of injectivity only by a factor of 2 following a 10-fold increase in viscosity. So you see that it's a surprise when you go to the field, depending on the expectations you have, and in that case, it's very likely that the expectations were built using a model, and so when you go to the field, you see that, well, the model has been a good tool, but it's wrong, and I have to update my understanding and my model if I want to go from a pilot to a larger field case. This case is really interesting, so you can find the publication. It's a Hillcorp Milne Point in Alaska, and what I want to show you here is the injectivity difference between tertiary polymer floods and secondary polymer floods. So in tertiary polymer floods, like this case, you can look at the conclusions. They say that the maximum 50% decrease in throughput right after the PF start. So they've lost 50% of injectivity switching from water to polymer, and when polymer was used as tertiary recovery method. So it's very interesting, and the idea is why. And Randy Seright's, for instance, explanation is that, well, we had viscous fingers, and now we are slowing down the velocity in these fingers because of the polymer solution, so we observe a pressure increase. But the most interesting part is when you look at polymer when used as secondary. And so in that case, the conclusions of the authors are that, well, ability to maintain pattern outputs, and there was almost no injectivity decrease and even very good injectivities all over, over the duration of the test and even the pilot. And so it means that polymer as secondary works better in that case than polymer as tertiary for many reasons, which makes sense. The fact that we minimize viscous fingering, we already have a better sweep efficiency, and so we displace more oil. And the most interesting, of course, result of that is no appreciable water production until 21% of pore volume in heavy oil, which is really, really, really important. So we're talking in this pattern about almost 1,000 centipoise oil without any injectivity problem, recoveries that are better than what is predicted by Buckley-Leverett, and water breakthrough after 20% of pore volume has been injected. So that's basically what the mathematics predicts when you look at Buckley-Leverett and everything. And so this is a very good reason to, I would say, to try to push for implementing any EOR technique earlier in the life of the field than later, just to avoid all the problems of viscous fingering, water production, and then fixing the issues with water production. So the conclusions for this couple of slides is why is the injectivity often much better than expected? And the reason is expectations. So that's very, very simple, is how do you build your expectations? So if you look at the papers before you screen your fields, you should not have much fear, because when you look at the literature, very few people have experienced dramatic injectivity decreases at the beginning of the project and even after some time, with the exceptions of heavy oil in some cases, when polymer was used as tertiary recovery method. And we just saw that when it is used as secondary recovery method, the problems are less. So that's probably also a good learning from these amazing field cases. So also something that's not really captured during, I would say, the design or understood is there is the simulation part. So in the simulation part, maybe the mathematics and the keywords can be improved. For instance, instead of using viscosity curves, we could use in situ rheology, because depending on the polymers, it can make a huge difference. Also, residual resistance factors are used from time to time, and we will see in another video that it can be very misleading parameters. In simulation, many people don't want to see or don't update the model to take into account the fractures or the extension of perforation versus time because of the water quality or of these aspects. So it's something which is moving, because if you inject polymer, you might extend the fracture. If you decrease the viscosity, it might close down. If you increase viscosity, it might open up. So it's something very dynamic that should be monitored and understood, and then maybe put into the model. So I said the polymer features are also very important. We said if you have fractures, it's very likely you will have no shear thickening. So my perspective would be to avoid to study shear thickening, and the best way for that is just to perforate more if you can in verticals, clean them, or to make sure that you have enough space or area for the polymer to enter the reservoir without being mechanically degraded. So it's a good way also to move faster from the lab to the field, is to start with the field, to do everything you can to be sure that there will be no degradation and a good connectivity between the wellbore and the reservoir. And so you skip these parts in the lab, you save time and money, and in the end you will get the results you are expecting, because it's still common sense, I would say. It's not black magic to enhance or to increase the number of perforations. And I think the most important part that I would say encompasses all of this are the near wellbore effects. So near wellbore effects, it's basically where everything happens: change in shear rate, very high shear to low shear, perforations, fractures, shear thinning, Newtonian plateau, and so everything happens in the near wellbore area, which is an area that's paramount to characterize if you want to minimize the I would say the problems you might observe. You need to work in teams, makes sense, but I don't see it still very much, which is a bit sad. And finally, there are things which remain that are being addressed, but it's going to be very difficult still, is modeling viscous fingering and polymer modeling. So we think we know how to model polymer, but again, the question is what we gather in the lab representative from what we have in the field? Do viscosity curves make sense versus rheology curves? Do residual resistance factor make sense? Does shear thickening make sense? Is the polymer solution the same in the lab and in the field? So these are very important questions which I personally don't see addressed very much in the publications that I have read so far, and would deserve more attention. And so with this, well, I hope it was useful, and if something's not clear, if I spoke too fast, but it's video, so normally we can slow it down, or if my English is terrible, well, I'd be very happy to answer some of the questions. And once again, more information, polymerflooding.com, and I'll be very happy to help if there is any challenge that you would like to address in your project. Thank you very much.